Good afternoon, everyone. I am Arpita Mishra. I am a PhD student in Indian Institute of Science, Bangalore, IISc Bangalore. Today, my topic is compact and highly efficient mid-infrared fundamental mode converter. Before going to the fundamental mode converter, I will talk a little bit about the mid-infrared design and why we are and how this mode converter will be helpful for sensing region. These are the outlines of my presentation: introduction, previous work on polarization converter, where I will be talking about some literatures, and then the polarization converter, the work which I have done, and then conclusion and future scope. So so to start with, mid-infrared is like 2 to 20 micron wavelength regime is known as mid-infrared. Mid-infrared regime. So generally we are going for mid-infrared regime because we want to sense gases. These are the trace gases which we should I point here?
The pointer, you can just use the PC because the pointer won't work on the LED.
Okay, fine. Okay, sir. So these are the gases which we will be sensing, that is carbon dioxide, carbon monoxide, nitrous oxide, nitric oxide, methane, ammonia, etc. So in one of our previous work, we have proposed the idea of a multi-analyte sensor. This converter is a part of that work. So this mid-air sensor is mid-infrared sensors have different applications like industrial, agricultural, environmental, and healthcare applications. So so in my work I have used germanium on silicon dioxide. Germanium as the waveguide layer, and silicon dioxide is the box layer, and beneath we have silicon wafer. Why? Because germanium has, as you can see here, germanium has the highest transparency transparency in the mid-air band, and that's why we have chosen germanium. And so let's talk something about the previous works which people have done on this mode converter. This is a mode converter where people have shown that soy based polarization converter, it works on rotation and transformation of the mode converter. This is around 25 and 98 micron long devices. Which is having, as you can see, this is having both vertical slot and a horizontal slot waveguide, and it is a T to TM and TM to TE converter with 99% of power transmission. Similarly, next one is this is a silicon waveguide, and this is asymmetric waveguide. As you can see, it is a staircase kind of structure. This is also silicon on insulator, that is SiO2 based structure, and polarization rotation is happening here in the asymmetric section. And in periodic interval, the periodic interval of the length of the converter, the T gets converted to TM and vice versa. And this is another slot waveguide based sensor where people have shown 92% of TM to T conversion. And here also they have used silicon on insulator, where here you can give the TE and you will get out TM on the other side. And this is a direct strip to slot waveguide mode converter where people have shown 96% of conversion efficiency with conversion efficiency with 220 nanometer of silicon layer. And this is a mode converter with microwave regime, TM to T polarization converter. And this is a adiabatic converter. As you can see, this is adiabatic mode converter, and this is also done in near IR regime. So next I'll be talking about this polarization converter which we have worked on. So this is our structure. Earlier you have seen a similar structure that that had both vertical and horizontal slot waveguide. Here we have used a vertical slot waveguide, where we will give the TM in the input, then we will get the TE at the output. So here you can see the in the picture that is around at the one, this is at the first place you will get the TM, you are giving the TM, and at the end you are getting the TE as output. And we have done some simulations like effective index versus waveguide width, and effective index versus slot gap simulations. And here you can see that the effective index of TE and TM are in the same similar range in this 0.5 to 1.2, around 0.5 to 1.5 width. So then we can use this part where this part where the TE and TM mode can be converted, because these are the hybrid modes in this point. And the same thing is happening at the slot gap around below 0.15. So these are the optimized parameters which we have used for the converter. This is W1 and W4 as shown in this figure. W1 and W4, which is 1.6 micron, and W2 is 0.8 micron. W3 is 0 nanometer. And T1 0.25, T2 is 0.25, and gap we have taken as 0.15. So we are getting 100% conversion from TM to TE. And this TM to TE conversion happens with this adiabatic mode evolution, which I talked about later before. So this by tailoring the geometry. So beyond 18 micron, which is shown in this second figure, beyond 18 micron, the TM rotates. It's the you can see it's the transition period, transition of the TM to TE. Then around 70 micron, it gets converted to TE mode completely. Yes. So this is the polarization conversion efficiency versus the mode number plot. Polarization conversion efficiency, polarization conversion efficiency is the is our fraction of transmitted light which is getting converted. So this tells us that the TM, the first mode, this is the fundamental mode, as you can see, the first mode is getting converted to TE. These simulations we have done using the mode expansion monitor in FDTD. And this is PCE and PER, that is polarization extinction ratio and polarization conversion efficiency plots with respect to wavelength. So we have done the simulation from 2.5 to 3.5, as this is our wavelength of interest. So as we can see, it's a broadband converter, but yeah, the conversion efficiency is not good in the starting, like around 20% it is. But as we are as it is going to, the wavelength is going to like 3 to 3.5 micron, it is getting getting higher, that is around 80%. And same thing with the PER also. And this is another geometry which we have used for this TE to TM converter. This is a two slot waveguides we have kept with these are asymmetric slot waveguides. Where we have, if we will give TE at one end, then we will get TM at the other. So here the effective index versus waveguide width simulation we have done. So this in effective index versus waveguide width, you can see that around 800 nanometer we have a overlap between the effective index of the TE and TM. Then we can, as we can say, this is a hybrid mode. At this point, we can use this 800 nanometer as our T to TM mode converter waveguide width, and the same thing with the waveguide height. So after doing some optimization, we did this. We got this optimized parameters where we are getting the highest results. That is here the efficiency is around 51%. These are the optimized parameters. That is waveguide one width is 0.8 micron. Waveguide 2 is 0.75. Waveguide 1 height is 0.35, and waveguide height second waveguide is 0.6. And length is 70 micron. Both our devices are 70 micron long, and here the efficiency is little less. It is 51%. Here what is happening here, as we know that in symmetric waveguides, TE and TM are orthogonal modes, so there will be no cross coupling involved. But when we will here we are involving asymmetricity, so when we are involving asymmetricity, at that time the cross coupling happens between the TE and TM. That's how our TE is getting converted to TM. And yeah, these are the results. Here also we are giving TE as the fundamental mode, and you can see that the 50% of TE is getting converted to TM, and these are the equations which we used. And here also you can see that the PCE in percentage we have given, and PER in dB we have shown that from 2.5 to 3.5. The PCE and PER you can see is varying from 15% to 55%, and the PER is varying from -1 to 1 dB. And the same thing is happening here. So here we have changed the source angle, and source angle from 0 degree, 1 degree, 10 degree, 20 and 30 degree, and the slot gap variation we have done from 190 to and 230 nanometer. So these are some results comparison which we did from the earlier literature. So earlier means people have shown the results for this wavelength of 1.55. In mid-IR also we have certain results in mid-IR, but those are using 2D material, so I have not shown that here. So here here our work is we are involving 2.5 to 3.5. That's a broadband design, and yeah, these are the references which we have used. Certainly our PER, that is polarization extension ratio, is not that high, which can be improved later. But as we means in our work we needed we needed the structure in the same needed the structure in the same let's say in the same on chip device. That's why we need this TM to TE converter, and that's the reason we are working on this. And this is the advantage which I have already mentioned. It can be integrated on the same platform. This is our prototype which we are planning to fabricate, which has a broadband grating coupler that is also published earlier. So this broadband grating coupler, and this has a wire waveguide and taper waveguide section, where then this part is the TM to TE converter we are using, and then here this is the slot waveguide based sensor where we will put the analyte, and then we can take the output, and yeah, this is the prototype which we are proposing. And yeah, this is the conclusion and future scope. So till now what we have done is it is primarily theoretical analysis which we have done, and there is always certain room for optimization, and there is certain room for improvement always. And to validate our findings, we have plans to to do experimental verification and fabrication in our Center of Nanoscience and Nano Fabrication Center in Bangalore. And yeah, hopefully that then we can validate the results with experiments. And yeah, this is the acknowledgement. I thank IEEE Sensors Committee to ask us to present our work. It gives us pleasure. And I also thanks Indian Institute of Science and IEEE Sensors Committee for supporting the necessary financial aid, which was really needed. And then I want to thank my lab members. This is my team, and my professor also is sitting here.
Thank you very much.